hopefully a few more people show up. So I did get some emails from people saying that because of weather they weren't going to make it. And that's a... I don't know. I guess it doesn't matter terribly if it is excused or not if you do that. Let's go ahead and start. Hopefully some more people will trickle in. So let's start by remembering the logarithm laws, because that's what we were in the middle of when we left, and that was a while ago. So let's start by just remembering those. So I have some stuff written on the board. Let's just see if we can remember on the spot. Flip to the previous page in the notes if you need the reminder. Fix any base b. What's the log base b of 1? 0, because you need to raise b to the 0th power to get 1. Log base b of b. 1. And maybe I should state right there's the constraint that that base b needs to be a valid base, so it needs to be positive, and it cannot be equal to 1. Log of a product. What's the log base b of x times y?
Log base b of x plus log base b of 1.
Yeah. So multiplication becomes addition outside of the logarithm. What about division?
Subtraction.
Subtraction. And in all of these, there's only one base, so if I forget to add a b in the base, no, it's base b. Exponentiation, log base b of x raised to the power of y. What is that equal to?
Log base b of x times y.
Yeah. Then that y is no longer in the log, so maybe it's helpful to put it before. And right, like you can multiply in either order, so it doesn't matter which side you put it on. So we definitely used a lot of those last time. If you have some equation that's like linear and a bunch of logarithms, well, you can combine those into a single log using these laws. Once you can combine it into a single log, you can rewrite the thing in exponential form. Now there are no more logarithms left. This is now like an algebraic thing to solve, you can solve it. With the caveat that you always just need to be careful with domain. When you do this step where you combine logs together, you might change the domain. It might become bigger than it used to be. So some of your solutions might be fake solutions. In this case, that -9 wasn't actually a solution. What I want to do today is do a few things with these two other formulas that we didn't explore in detail last time, the change of base formulas. So these change of base formulas say that you only really need to know a single base for logarithms and exponentials. You can get everything else by using just your one favorite base. If you have a base you don't like, log base a of x, you can rewrite that as the log base b of x divided by the log base b of a. That base b can be any base you want. So if you have a calculator that only walks base 10, that means you don't need to care that you can only walk base 10 in your calculator. If you want to walk base 3, just ask for the log of whatever input you want, divided by the log of 3. Maybe color coding is useful here. The thing inside the parentheses winds up on top of the fraction. The thing in the base winds up in the bottom of the fraction. And there's also a change of base formula for exponentials. And what that formula says is you only need to walk in your favorite base. In practice in calculus, this will mean you'll want to walk base e all the time, because if you're doing calculus, you should be base e. In this class, well, it depends on what the context is. If you want to walk base 2, walk base 2. If you want to walk base 10, walk base 10. The formula says that a to the x can be written as an exponential with base b raised to the power of x multiplied by the log base b of a. So it says if you want to walk base, any base you want, base 10 if you want, you can. The only cost is you need to be willing to multiply in the exponent by a log of it. That seems pretty okay. All right, let's use that for something. Now I'm going to get into what the notes actually have in them. So let's start with this. So there's like two things here, so let's do everything before the end. So let's use the formula we just got to rewrite pi raised to the power of x plus 1 in terms of base 10. So let's start with that. So that first one, pi to the x plus 1. I want to write it as something in base 10. And let's try to use this formula. So the thing in the exponent is going to stay in the exponent. So what's the thing in the exponent and the thing we're starting with? X plus 1. So it's going to be an x plus 1. Ooh, and I'm going to, make an unforced mistake. There's an intentional error I'm about to make. And what do I need to multiply that x plus 1 by?
Log base b of pi.
Need to multiply it by the log base b of pi. And what base do I want to do? Well, what base am I walking in?
Base 10.
Base 10. Yeah. And if you want to leave out that base 10, most of the time I'll follow the convention that like, if there's no base 10, it's base 10. So I said I made a mistake. What did I do here that's wrong? Yeah.
Shouldn't it be just 10 to the x, not x plus 1?
No, so whatever the exponent is here, so if you wanted 3 to the 7th, you could rewrite that as 10 to the 7th. So whatever it is that's in the exponent has the role of x here. So since it's an x plus 1 in the exponent, there should be an x plus 1 there, so I don't think that's the
Parentheses around x plus 1, you're multiplying it by log base 10.
Yeah, great. I need everything in that exponent to become multiplied by. Right now it's just the one that will get multiplied by. All right, so there's prompt 1. Let's use that to solve prompt 2. So if I want to solve pi raised to the x plus 1 equals 10 to the x. Well, I could rewrite it in terms of any base I wanted to, but I've already rewritten it to be in base 10, so let's use that. So using the result from step 1, this becomes 10 to the power x plus 1 times log base 10 of pi equals 10 to the x. That seemed like a sensible step. Everything now has just like a single base. Cool. What can I do with this now?
Put the exponents equal to each other.
Yeah. The only way 2 powers of 10 can be the same is if the powers are the same. So, this means that x plus 1 multiplied by log base 10 of pi has to just be equal to x. And let's just make note of what sort of equation this is. So this quantity, log base 10 of pi, that's just a constant. If we wanted to get a decimal approximation, we could. In fact, let's get a decimal approximation. I don't think I'll use it. Oh, is it doing the thing where that screen gets out of focus every time I put my hand underneath? It's because I haven't pressed this button yet. Now it should be fine. Log base 10 of pi. Well, what am I doing? It's base 10. Everything defaults to base 10. Log of pi is around 0.49. So whatever this constant is, this is some constant it's about 0.5. So what type of equation is that? What's the most complicated thing you see having to do with the x? Like I see x raised to the power 1, then it's added to 1, then it's multiplied by a constant. The constant has a complicated name, but it's just a constant. And then that's set equal to x. That's a linear equation. So we have like a strategy to solve those, right? Try to like get everything involving x onto one side, everything not involving x onto the other side, and go from there. So what would you want to do to this if you wanted to solve it?
Divide by x plus 1.
We could divide both sides by x plus 1. I think I'm going to do that and we'll decide whether it's an improvement or not. So let's see, if we divide both sides by x plus 1, I'll see log base 10 of pi equals x over x plus 1. Is that better or worse?
That's just worse.
I think it's worse, right? There's like, now there's a denominator with a variable in it. So it's not a wrong step, but I think it's a bad step. So I'm going to take advantage of the fact that I have erasable things. So let's not do that. What would be a... So I do want to get eventually the x's all onto the same side, but I don't think division's the way to do it. Yeah.
Would you be able to distribute the x plus 1?
Absolutely, we can distribute. Let's do it and see if it buys us something. So that'll get me x multiplied by log. Well, you know what? Maybe I'll see this. How many people would prefer to walk with that blue decimal approximation? Cool. I'll do that and then I'll fix it so that we actually get an exact value. So let's distribute. 0.5 plus 0.5 times 1 is 0.5 is equal to x. All right, what would you want to do next? So remember, the goal would be like getting all the x's onto the same side, then figuring out what we need to divide both sides by in order to get x on its own. Could subtract that 0.5x to the other side. That seem reasonable? Let's see what happens. So x minus half of an x. Let's see, that'll give me 0.5 equals 0.5 times x. Right, because 1 minus 1/2 is a half. I've used like purple there because I want to eventually replace these approximations with exact values. All right, what next? Yeah, if 1/2 is equal to 1/2 x, then what is x equal to? Yeah, but just like say it louder. Everyone's being very quiet.
1.
Yeah, right. Let's divide that 1/2 to the other side. I'm going to write something silly. I'm going to write, so that means x equals 0.5 divided by purple 0.5. And all of those were actually like approximate, right? Those 1/2s weren't really 1/2. They were just pretty close to 1/2. So the final answer is pretty close to 1. I'm going to change all this work to actually get exact values. So these, like, blue 0.5s, what are they actually equal to?
Log base 10.
Log base 10 of pi. So let's just replace all of those with log base 10 of pi. I'm going to use the fact that I have something erasable. So x times log base 10 of pi plus log base 10 of pi. And then we subtracted this over to the other side. So this blue 0.5 is still log base 10 of pi. So far, so good. That purple 0.5 isn't log base 10 of pi anymore. It's 1 minus log base 10 of pi. Because it was 1x minus that many x's. All right. So, now let's get an actual honest to God exact value for the answer. So what is x equal to? Yeah.
How many decimal places do you need?
I want an exact answer, so no number of decimal places will be enough.
Oh,
But what did you type into the calculator to get your decimal approximation? Because that is what I want.
well, I did the log base 10 of pi, but I just used the actual value throughout the entire math.
Cool, so let's just put that in. So it's log base 10 of pi. And then what did you divide it by?
Well, I just turned the log base 10 of pi into the full decimal, and then I used that when I was doing my math.
Oh, cool. So you got a better approximation, but it was still an approximation. So you used like however many 10 digits that the calculator spits out.
Mm-hmm.
So you're probably accurate up to like at least 9 digits, which is pretty good. But I want a full-blown exact value. And then we'll see if it agrees with what you found. So I want to just divide that thing in purple over to the other side. Which agrees with what you did, right? Your last step is like you divided by like whatever 1 minus that 0.49, etc. was.
Yeah.
So let's just divide by it. 1 minus log 10 of pi. And allegedly this should be pretty close to 1. And let's just see if it is, and let's see if it agrees with the decimal approximation you got, because it should. So I'll pull up the calculator I like to use. If you all have a calculator you want to use, go for it. So let's do log of pi divided by 1 minus log of pi. That's pretty close to 1. That agree with the more decimal places that you got?
That's what I got.
Awesome. Yeah, cool. So, it's pretty close to 1. But if we wanted a decimal approximation with more precision, there's no like stated precision here, so maybe I'll go 0.989 because that last 8 will round up because of the 6. Feel pretty good? Nice. And I'm pretty sure WebWorks going to ask you to do something basically exactly like this. And WebWorks pretty picky about how much precision it wants in its answers. So, like, the answer of 1 would definitely not have been good enough. Probably 0.989 wouldn't be good enough. You said you had like 9 digits or something. You probably would have been happy with that. You don't have to worry about that. You can find exact answers. That feel pretty okay? This procedure seems sensible? So the idea is the change of base formula lets you change an exponential with 2 different bases into an exponential with only 1 base. Once you have an exponential with only 1 base, you can just get rid of the base. And once you get rid of the base, in this case, you just have a linear equation with some complicated looking constants, but just a linear equation. Those are straightforward to solve. Nice. All right, so let's muck around a few more things. Let's make a graphing exercise. So, let's do this. So this is going to be the exact same question as is in the previous one. Well, essentially the same question. Express 3 to the x in terms of an exponential with base 2. So 3 to the x is equal to 2 to the what goes in the exponent?
X.
And anything else?
Or log base would be 2x.
Let's just check out the formula. So there's the old base. So in this case, the old base is 3. The new base is 2. So the x becomes an x. So far, so good. And it should be the log base new base. So that new base is 2. And the thing in the parentheses is what the old base is. What was the old base?
3.
3. All right. And I've provided a decimal approximation. Log base 2 of 3 is about 1.58. So let's just look at that. So that's pretty close to 2 to the x multiplied by 1.58. Gesundheit. I want to make a quick, graphing conclusion here. What happens to the graph of a function when you multiply the input by 1.58? Gesundheit. So I'm doing something to the input, right? So it should do something horizontally. What happens when you multiply the input of a function by a number?
Increases.
What increases?
Well, the x value.
Cool. So it's going to do something horizontally, and it's like multiplying. So it's either going to do a compression or a stretch. And since it's happening next to the x, it'll do the opposite of what's intuitive. It looks like it should expand because you're like multiplying x by something. It'll do the opposite of what you expect, so I think it compresses. So this will do a compression horizontally by a factor of 1.58. Approximately. So let's write down an actual honest-to-God conclusion. So the graph of 3 to the x is the graph of 2 to the x with a horizontal compression. So with that in mind, here are 2 graphs. I want you to now tell me which one of those should be the graph of 2 to the x, which one should be the graph of 3 to the x. And let's use this sentence to decide. Which one of those looks like it's the horizontally compressed version of the other? B is the compressed one. Oh, cool. So which one should be 3 to the x then?
The 2 x.
Nice. So B should be the graph use the color coding. So the graph of 3 to the x should be the same as the graph of 2 to the x with a horizontal compression. B is the graph of A with a horizontal compression. So process of elimination, if one of those is 3 to the x and the other one is 2 to the x, they have to be like that. That feel pretty okay? Let's go ahead and check this fact. So I'm going to pull up a Desmos graph real quick. So let's graph 2 to the x. Let's graph 3 to the x. Does it look like the blue graph is a compressed version of the red graph? Horizontally compressed? Awesome. That's all we were saying. And let's even check that this is the same thing as 2 raised to the x multiplied by log base 2 of 3. God damn it. Green look like it lines up pretty good with blue. Cool. All right. Let's play the same game with the change of base formula for logs. So using the change of base formula for log, we write log base 3 of x in terms of log base 10 of x. Yeah.
Would you divide, would it be log base 10 of x divided by log base 10 of 3?
Awesome. Yeah. So whenever you have a base you don't like, in this case the base we don't like is 3, you can put it in terms of a base you do like. So the old base goes inside of the log in the denominator. The new base is just the new base. The thing in the parentheses is the thing in the parentheses in the numerator. And let's check this again by, I know that there's a graphing example on the next line, but log base 3 of x. Let's also graph the log base 10 of x divided by log base 10 of 3. Black and purple seem to line up pretty good. All right, so I think the identity is at least graphically verified. And let's use one thing here. So I'm going to get a decimal approximation for that log base 10 of 3, not 44. So this is pretty close to just being log 10 of x divided by 0.48. So let's think in terms of graphing. What happens to a graph when you multiply the output, when you divide the output by 0.48-ish? What does dividing a function by 0.48 do to the graph? And it's like a mild trick question because like I'm dividing by something less than 1. So let's rewrite that just a little bit. So that's 1 over 0.48 times log 10x. Without using a calculator, 1 over 0.48, what is that pretty close to? Yeah, but what's 1 over a half? 2. So if you don't like that, then we can actually use a machine. 1 over log base 10 of 3 is around 2.09. So it's about 2.1 times the log base 10 of x. All right, so now let's ask this question. What happens when you multiply a function by 2-ish? What happens to the graph? Let's see, I'm multiplying something by the output value of a function. So something will happen to the y values. And I think it'll either be a compression or a stretch.
Stretch.
Yeah,
Yeah.
Yeah. yeah. So it should, so let's write that down in a sense. So log base 3 of x is the same as y equals log 10 of x with a vertical stretch. All right, so log base 3 of x should look like log base 10 of x, but with a vertical stretch. So log base 3 of x should be taller than log base 10 of x. So same multiple choice question. Those two graphs, if one of them is log base 10 and the other one's log base 3, which one's log base 3?
B.
because that's the one that looks vertically stretched. Cool. That all feel pretty nice? And again, like, if you wanted more intuition there, you could literally graph those two things using a machine and see if that agrees with that intuition. And here's the last one that I want to do. So this last exercise is going to be very similar to what I'm going to ask you to do in an open-ended problem. The one theoretically posted for like the Friday before spring break, but it's really posted for today now. Compute for me the log base 2 of 3 times the log base 3 of 2. And let's not use a machine for it. We can if we want to get it like an intuition. Let's try to think through it using these logarithm laws. So it's annoying that there are 2 different bases there, right? Do there need to be 2 different bases? We could rewrite both of those using our favorite base, any base we want, and it shouldn't really matter what base. Maybe the walk will be easier if we pick like an appropriate base, but let's just pick a base. What base would you want to rewrite this problem in terms of?
10.
Base 10. It's a good, solid, obvious choice. Base 10 is a reasonable choice. I don't think it's the easiest choice, but let's use base 10. So let's rewrite everything here in terms of base 10. So let's rewrite log base 2 of 3 times log base 3 of 2 in terms of base 10. Let's do some color coding. Log base 2 of 3, what is that in base 10? Let's see, the change of base form is that should be the log base 10 of something divided by the log base 10 of something. What goes in those 2 parentheses?
3 and 2.
Awesome. Let's also do this one. Same question, but log base 3 of 2. What goes in the parentheses on top?
2.
And on bottom?
3.
All right, cool. So let's look at that for a second and see if we see anything. See anything useful there? Simplification to make? Let's see. Whatever log base 10 of 3 is, it's a number. In fact, we've seen that it's about like 0.5-ish, but let's not use that. I also divide by that same number. What happens when you multiply by a number and then divide by that number?
It's the same.
Yeah, those 2 things will cancel out. So let's do some canceling. So that'll leave me with log base 2 of 2, log base 10 of 2 divided by log base 10 of 2. Does anything cancel there? Yeah, so it looks like just everything cancels. So what are you left with? Just 1. Nice. So whenever you see a bunch of different logs multiplied together, try getting it all down into a single base. Hopefully something nice will happen. No promises that it will. Sometimes things are just complicated. But in this case, things simplified nicely. And if you wanted to check that, you could now check it. Let's check that that's correct by now using a machine. Use a machine for me and compute for me log base 2 of 3 times log base 3 of 2. This will be a more meaningful exercise for some than others. I don't know, maybe I'll play along too. Google Calculator is a little bit bad with logs and multiple bases, so I'm going to use Wolfram Alpha. Log base 2 of 3 times log base 3 of 2 is 1. That agree with people who used a calculator? All right, cool. So the reason I did that last little double check is whenever you have something complicated and you do some algebra to simplify, see if a machine agrees, right? Like you did the walk yourself, but you can use a machine to check. All right, so we have these logarithm laws. I'm not going to bother rewriting them here. We have them on the board. Let's keep on using these to solve things. I'm going to hopefully get to a few applications on the next page. All right, so these first three might feel familiar, but that's okay. If you want to solve log base 3 of 3x plus 5, that look like something you know how to solve? Let's see, how many logs are in the formula? Just 1. And all the unknowns are inside of the log. So it's like the useful thing we did last time in this situation. How could we get rid of that log? I say the word logarithmic form. Does that give you any ideas?
We just make it equal to 3 negative 1.
Yeah. So when you rewrite an exponential form, you take the base in this log, that becomes the base in an exponent. And the exponent of that exponent is the thing that used to be on the other side. So we get 3x plus 5 is equal to 3 to the power of negative 1. I don't know that's hard to read now. That negative 1 is in the exponent of the 3. That look like an easier equation to deal with? Yeah, because what does 3 to the power of negative 1 mean? What is 3 to the negative 1?
Negative 1.
Positive 1 power.
Or positive 1.
Yeah. So this is really just 3x plus 5 equals 1/3. That look like something you know how to solve? In fact, if I just stall for a few seconds and maybe let you consult with each other, do you think you can solve it? Well, everyone's doing it, so that's good. That makes me happy. All right, so let's hear it. What answer are people getting?
Yeah, negative 1.5.
That sounds approximate. X equal x about, you said negative 1 point.
1.53 repeating this.
Oh, okay, now it's an exact value. That agree? Anyone get an answer in the form of a fraction instead? What'd you get?
Negative 14/9.
Cool. And yeah, I guess that looks right. 14's about halfway between 9 and 18, so that's about negative 1.5. Those two are consistent. Anyone want to talk through that in any more detail than the none that I provided? Cool. Then I'm just going to do one thing. Let's check by looking at a graph. So it looks like there's a single place where y equals this function and y equals negative 1 cross. Does that agree with what we found? Yeah, that maybe makes me doubt this decimal approximation because it disagrees with that one.
That's what I got
That's what
in my calculator.
Oh, okay. Okay, so I just wrote it down wrong, did I?
6.
So I think Desmos, anyway, is suggesting that. Let's see if that agrees with this fraction. Negative 14 over 9. Ah, it's in fact the 5 is repeating and the 6 is from the rounding up. Cool. Should we go through any of the algebra? People feel good? Nice. So, if you see an equation involving only one log, you can get rid of that log, rewrite in exponential form. And I think with the remaining time, let's talk about one of these two remaining ones. 2 or 3. People have a preference? 2? 3? Cool. Let's do the 2 because I think I saw one more vote for 2. And like this looks very much like something that we did last time. I don't think we did any LNs last time. Not that it's like that much more complicated. So let's see, I see lots of different logs in this problem. Like 3 different logs. I'd kind of like to get like maybe all the logs combined into one log, or at least all the logs on each side combined into one. Can we do that? I think so. Let's just look at what we see outside of the log. I see a 2 there in front of that ln of x plus 1. What can I do with that 2 to make it go inside of the log? I see a number times a log. That number can go in the exponent. So let's do that. That first bit will become ln of x plus 1. And then it'll be squared. All that inside of the log. So I need all these extra parentheses to make sure I'm taking the ln of the right things. Minus ln of x plus 2 equals ln of 2. All right. Then maybe I'll see what people would like. I'm planning on just like leaving this ln of 2 on the other side. Would anyone prefer if I put it over onto the left-hand side by subtracting it? Okay. Let's see what happens if we don't. So let's worry about this subtraction. All right, I'd like to combine those 2 logs into a single log. Can I? Yeah, what does it become? Division, great. So this will become ln of, maybe I'll even FOIL out this thing in the numerator, x squared plus 2x plus 1. All that divided by x plus 2 equals ln of 2. All right. So we have just ln of some stuff equals ln of some stuff. What can we do with that equation?
We can make those values equal.
Yeah, I'm pretty sure you mean the right thing. What do you mean by those values?
Inside the parentheses.
Yeah, awesome. Log is a one-to-one function. It passes the horizontal line test. So the only way log of some stuff can be equal to log of some stuff is if the stuff on the inside is equal. So x squared plus 2x plus 1 divided by x plus 2 is equal to 2. That feel pretty good? All right, what should we do next?
Cross multiply.
Cross multiply. Right, that seems helpful. I see x is in that denominator. I'd like to not. So let's multiply that over to the other side. Maybe I'll do the distribution all at once. X squared plus 2x plus 1 equals 2x plus 4. I do that right? I did like 2 steps in one. People happy? All right, what next?
Combine or move everything on the side and back.
Cool. Yeah, let's move everything to the other side. Guess that'll mean subtracting the 2x from both sides, so those will go away. x squared minus 3 equals 0. Trucking along. What next?
Add 3 on both sides and square.
Oh, I guess the opposite of squaring.
Or,
You probably meant that, I think.
yeah. Square.
Cool, so it looks like I get two solutions, x equals plus or minus root 3. Should I do is there anything I still need to do, or is that just the answer?
So you're gonna check if, go back to the original equations and check if that's true or not.
Yeah, so I need to like check if things are in the domain. So, let's do a quick domain check. So I see an x plus 1 inside of an ln. So I better have x plus 1 be positive. I also need x plus 2 to be positive, and I need 2 to be positive, but 2 is positive, so there's no issue there. If x plus 1 has to be positive, then what can you tell me about x? Better be bigger than negative 1. And x also has to be bigger than negative 2, but if it's bigger than negative 1, then it's bigger than negative 2. So that's the only constraint I have to worry about. Are both of the solutions we just found bigger than negative 1? Which one's not?
Negative 3.
The negative 1 isn't.
Or negative 1.
Yeah. The negative square root of 3 is not. The negatives, yeah, okay, cool. So there's only one solution, it's the square root of 3. We feel pretty good? All right, so with 3 minutes on the clock, I think I want to at least discuss some applications that we'll explore in more detail next time. Let's talk about carbon dating a little bit. So I guess this is really like down here. Okay. So, one of the things that exponential functions model are things that decay radioactively. And the reason that they decay radioactively is because if a thing decays radioactively, really what that means is some proportion of a quantity of that thing will break down into simpler elements in a fixed amount of time. And that fixed amount of time is the same depending on what element you're looking at. So, uranium-238 has a half-life of 70 years. That means every 70 years, half of a sample of U-238 will decay into whatever it is that U-238 decays into, not a chemist. So there's a relevant formula here. If you start with some initial quantity of a radioactive substance and wait that some amount of time, well, you just need to figure out how many times you divide by 2 and then divide by 2 that number of times. So, if lambda is the half-life, that's the amount of time needed for half of the material to decay. So, how many half-lives go by in some amount of time? Well, it's that. So that thing underlined in red is the number of half-lives. And each time a single half-life goes by, you divide by 2. Division by 2 is multiplication by a negative power of 2. Divide by 2. The right number of times. And what are you dividing by 2? You're dividing whatever the initial quantity is. So let's just make a quick model. So, U-232 has a half-life of 70 years. So that means that the half-life of this radioactive isotope is 70 years. So that's the thing that gets called lambda. If you take 1 kilogram, so there's some initial quantity, how long does it take to decay down to 1 gram? Well, what does that mean? I need to figure out how long does it take. So I want to solve for t. I would like to know a time. And what do I need to solve? initial quantity, so 1 kilogram, is equal to, nope, 1 kilogram is the initial quantity, times 2 to the negative t divided by half-life. And I would like to know when that is equal to 1 gram. I don't actually have any time left, but does that look like something that you have some tools to figure out how to solve that for time? Yeah, those of you who are, we're not going to do it right now because there's not time, but what's like the story you would want to be how you would solve that for time? Yeah, I guess there's like the one sentence story. Somehow logs are better useful here. I want to get rid of an exponential. How do you get rid of exponentials? You take a log. So this is what we'll start in on next time.